So first point in an isothermal process is it's a slow process.
Write it down on the phone.
Point number 2, isothermal. Iso refers to same. Thermal refers to temperature. So there is no change in temperature. So the process happens at constant temperature, or in other words, change in temperature is 0. Right? This also translates to change in internal energy of the gaseous molecules is 0. Because whenever temperature is raised, the gaseous molecules will gain kinetic energy.
Right.
That will appear as increase in internal energy.
Yes.
Similarly, when temperature is decreased, then that will appear as reduction in kinetic energy of the molecules.
Right.
That will be observed as decrease in internal energy of the molecules. Right?
Yes.
So if there is no change in temperature, therefore there is no change in internal energy of the molecules. Is that clear?
Yes.
Usually, if you see, according to first law of thermodynamics, the quantity of heat that you provide to the system will be used up for two purposes. One of the purposes to change the internal energy of the molecules, and the other one is to do some work. All right. Let me give you an example for this. Let's say there is a cylinder. You're supplying some heat to the system. Let that heat be Q. You have a piston. Right? You have gas molecules inside. Okay. Now, what is going to happen is you're supplying this heat. What will it do? Usually, this will increase the temperature inside, or in other words, it will change the internal energy of the system. Plus, part of that energy will be used up in moving the piston.
Right.
You know that heat causes expansion, correct?
Yes, sir.
So the piston probably will move from this position to a new position, let's say. Let's say the piston moves to a new position. So some work has been done, correct? The piston has moved, right?
Yes, sir.
Yeah. So this is what is summarized in this first law of thermodynamics, which says the total quantity of heat supplied is used up for two purposes, right? One is to increase the internal energy of the system, and part of that energy is used up for doing some work. Is that clear?
Yes.
But when it comes to isothermal process, I've already told you there is no change in temperature, right?
Yes, sir.
Because of that, there is no change in internal. So this part will become 0, right?
Right.
So the quantity of heat that you supply is completely converted into work.
Yes, sir.
In an isothermal process. Right?
Yes, sir.
Okay. So let's look at another process called adiabatic process. It's a rapid process. The process happens so fast. Right? So here what is happening is there is no heat exchange. Between the system and the surroundings. All right. So what is the meaning of that? Let me give you an example here. Let's say we have a cylinder. There is some gas inside. You have a piston. Let's say you're applying some pressure from the outside and compress and pushing the piston in. All right.
Yes, sir.
And you're doing this very fast. So when you're doing this very fast, right? Let's see what happens. So when you're compressing the gas, right? Correct?
Yes, sir.
So when you compress the gas, what is going to happen is there will be some heat generated, correct?
Correct, sir.
Right? Now this heat which is generated, because the process is very fast, this heat cannot dissipate to surroundings.
Yes, sir.
So here your gas inside plus the cylinder, we call it a system. And the outside world, we call it as surroundings. Clear?
Yes, sir.
Yeah. So I repeat the process. You are applying pressure from outside. You're pushing the piston inside very fast. Now, when you do that, because of the compression of the gas, there is going to be heat generated, correct?
Correct, sir.
But because it happens in a short duration, this heat does not have the time to go from the system to the surroundings. Is that clear?
Yes, sir.
So what is going to happen now? All that heat which is generated within the system is absorbed by the gas molecules.
Right.
So what will happen is the quantity of heat that is generated is absorbed by the molecules, which reflects as increase in internal energy.
Right, sir.
Right? So change in internal energy will happen. And what is going to happen to the temperature?
It
Temperature
also rises.
Yes, temperature also rises. Is that clear?
Yes, sir.
Okay. So if you go by this equation, or in other words, delta Q is equal to delta U plus work done. Here what's happening is delta Q is 0. Why is delta Q 0? There is no change in heat. The extra heat that is generated is completely absorbed as what?
Yes, sir.
Increase in
Internal energy.
So this becomes 0. So your work done is equal to minus delta U. So the amount of work that is done on the system is getting absorbed by the molecules.
Right.
To raise their internal energy. Is that clear?
Yes, sir.
Yes. So these are a couple of points that needs to be noted. Of course, isothermal process, PV is equal to nRT for an ideal gas. Your PV power gamma is a constant. The equation for adiabatic process is PV power gamma is a constant. So what is gamma?
CP by CV.
Cp divided by Cv. Specific heat capacity at constant pressure divided by specific heat capacity at constant volume. So how do you keep pressure constant and how do you keep volume constant? if you see in a system, okay, when I keep volume constant, I call it as isochoric process.
Right.
So how do you keep my volume constant? I fix this. Now what happens? There is no scope for the piston to move, correct?
Yes, sir.
So if the piston doesn't move up, let's say, let's say I'm going to supply heat. So I'm supplying heat. All of that heat is going to convert into increase in what? Internal energy of the system. There is going to be no work done because the piston cannot move. Why the piston cannot move? Because I have clamped it here. Is that clear?
Yes, sir.
So this is how I maintain what?
Volume is constant.
Is that clear?
Yes, sir.
So when volume is constant, piston cannot move. If piston cannot move, the work done is what? So work done in an isochoric process is zero. Work done can also be written as pressure into change in volume. Because you know, right? Work done can be taken as what? Force into displacement.
Yes, sir.
So if I divide by area and multiply by area, right?
Right.
What is force by area? Pressure. Displacement into area, volume.
Yes, sir.
Yes.
Yes, sir.
Force in delta is I can write. So this becomes delta V. So P into delta. Clear, Samuel?
Yes, sir.
Next is what? ISO.
Bharik.
What do you mean isobaric process?
And that's the case where pressure is constant.
Yes. How do I maintain pressure as constant? Very simple. If I don't clamp the piston, pressure automatically is constant. I just leave it the way it is. We have gas molecules here. We are supplying some heat to this system. Now, what do you think will happen? Some part of the heat will be converted to
Internal
increase in
energy.
temperature and increase in internal energy, right?
Yes.
Now, what happens is the moment pressure builds up inside, right? As temperature increases, pressure builds up inside, correct?
Yes, sir.
Once pressure builds up inside, the pressure inside the system is more than the surroundings, right?
Right.
And it always moves from high pressure area to low pressure area, correct?
Yes, sir.
So inside the system, because of the heat that you supply, pressure is increasing now. Outside, atmospheric pressure is less than that, right?
Yes, sir.
So there will be pressure on the piston in this direction, correct?
Yes, sir.
So piston will move up. Are you able to understand?
Understood, sir.
So how long will the piston move up? It will move until the pressures on both the sides, outside as well as inside, become same.
Same.
So that's how you maintain pressure as constant. Is that clear to you?
Yes, sir.
Yes. Okay. Okay. These are some basics on, the
Thermodynamics.
physics part of thermodynamics, which is common in chemistry also.
Right.
All right. Now, one difference in the way you write the equations in physics and chemistry is in first law of thermodynamics, I gave you an equation, right? The
Yes.
quantity of heat that you supply is converted into increasing the internal energy.
Plus work
The
done.
amount of energy is used up for doing work, correct?
Yes.
So in physics and chemistry, the sign for work done is a little different.
Okay.
In physics, work done by the system is taken as positive. That means system does some useful work, right? You take it as positive.
Yes.
Work done on the system, you take it as a negative. So what is the meaning of this? Suppose you are providing heat. Because of that, the gas expands, right?
Yes.
And this puts pressure on the piston and it moves up, right?
Right, sir.
So this is what. So the piston is moving up. Did you pull the piston up or the gas pushed the piston up?
The gas pushed it just enough.
Yes, so that is called work done by the system, correct?
Right.
So that will be, this work done will be taken as what?
Positive.
Yes, in physics. Suppose, let's say you are applying pressure on the piston and you are compressing the gas, let's say.
Work done on the system is negative.
Yeah, so you are doing work on the system, so you take it as negative. In chemistry, it is the opposite.
Okay.
In chemistry, work done by the system, you take it as negative. Work done on the system, you take it as
Positive.
positive. So it's just a convention, but concepts remain same.
Right.
Only that aspect you need to watch out for.
Right.
Okay? Because one thing is clear, then the other one is automatically the opposite.
Right, sir.
Okay? Fine. Now we'll move on to thermochemistry part. So first we will, understanding thermochemistry through numericals is the best way. Okay?
Okay, sir.
So let's do a worksheet on this. All right? First question. First two questions, if you see, are from thermodynamics part of it. Remaining questions are from thermochemistry. So the thermodynamics part of it, you may get it for a mark or two. But part of detailed answer questions, you will have the
Okay.
thermochemistry part.
Yes, sir.
Okay, anyways, we'll do both of them. An ideal gas expands from 10 power minus 3 meter cube to 10 power minus 2 meter cube at 300 Kelvin against a constant pressure of 10 power 5 Newton per meter square. What is the work done? Can you think about it?
Yes. So here pressure is constant as given in the sum.
Yes, pressure is constant, correct?
Right.
Some issue with my writing pad. Just give me a minute. It's okay now. Okay, but now tell me, ma. So work done. I've told you what it is. What pressure into change in volume.
Volume.
All right.
Yes, sir.
So what is the pressure?
Pressure is 10 power 5.
Right. And what about the volume change?
From 10 power minus 3, it's gone to 10 power minus 2.
Yeah, so the initial pressure is 10 power minus, sorry, initial volume is 10 power minus 3. The final volume is
10 power minus 2.
it's 10 power 5. Or out of that 10 power 5, keep 10 power 2 in. Let's say I keep 10 power 2 here. I take 10 power 3 inside. So I'll get 10 power 3 into 10 power minus 3 minus 10 power 3 into 10 power minus 2. So what is 10 into 10 power minus 3? 1.
1.
What is 10 power 3 into 10 power minus 2?
10 to the power of 1.
10, right?
That's what, 10.
The powers. So you get minus 9 into 10 power 2. So that's nothing but 900 joules. Or in other words, or I can write minus 0.9 kilojoules. Is that clear?
Sure. Yes, sir.
Yes, sir. So as you can see, right? What has happened here? Here, expansion has happened, right?
Right.
10 power minus 3 is what? Less than 10 power minus 2, correct?
Correct, sir.
So work done, as far as in physics, usually we take it as positive, correct?
Correct, sir.
In chemistry, you get a negative answer. Anyways, here you can see the usual convention of physics has been given in this option.
Right.
So you will take 0.9 kilojoules.
Okay, sir.
Watch out for that. Please take it down.
Done, sir.
Taken down, Samuel?
Yes, sir.
Yes, okay. Next question. The work done by a system is 8 joule when 40 joule heat is applied to it. What is the increase in the internal energy of the system? Would you try answering this yourself?
Yes, sir.
All information required I have given you. Yes, Amber.
So is it 32 joules?
Are you confident or you're doubtful?
Confident, sir.
How can you explain?
So here they've given the work done by system as 8 joules and the heat supplied to it is 40 joules. Now they're asking the increase in internal energy of the system. So increase in internal energy of the system is amount of heat supplied to that system minus the work done by that system. 40 minus 32 joules.
Yes, right. Because you know that the quantity of heat that you supply will be used up for two purposes, right? What is it? One of them is?
For the change in internal energy.
Yeah, it will increase the internal energy of the system. Plus it will do what? It will move the piston up, correct?
Yes, sir.
So that is nothing but your work done, correct?
Yes, sir.
So 40 joules you are given heat. 8 of it is used for work. So the remaining 32 must be used for?
Internal energy.
Yes, exactly. So is it clear now?
Yes.
Very good. Now we come to the energetics part or thermochemistry part. Okay.
Right.
So you have something called heat of combustion. You have something called enthalpy. enthalpy of combustion, enthalpy of neutralization, enthalpy of hydration, enthalpy of solution, correct?
Right.
But all these have the same concept, okay? So once you get the concept, all these definitions are very, very similar, okay?
Yes, sir.
At least 2-3 of them I will explain first, and then we'll move on to the questions, okay?
Okay, sir.
First, enthalpy of formation. Enthalpy always means heat change,
Right.
okay? For example, let's say, enthalpy of formation of a compound, let's say calcium carbonate. So whenever I use the word enthalpy of formation, see, the actual method of preparation might be, to heat calcium oxide with carbon dioxide.
Right.
But you should not write this equation for enthalpy of formation. Whenever I say enthalpy of formation, what I mean is enthalpy of formation compound from its basic elements.
Right.
So what are the elements in calcium carbonate?
Calcium, carbon, and oxygen.
Yes. So the way you write the equation is calcium plus what?
Carbon plus oxygen.
Yes. Is that clear? So of course balancing you can do, right? By balancing we just multiply 1.5 here. It's a balanced equation, correct?
Yes, sir.
Because one calcium atom is there on both sides, one carbon atom on both sides, three
Yes.
oxygen atoms on both sides.
Yes.
And 1.5 into 2 is 3, right?
Yes, sir.
Okay, here, can I multiply it 2 throughout and make this not keep it as 1.5, but make it 3? Recommendation is no, okay?
Okay.
Why is the recommendation no? Because whenever I say enthalpy of formation or any enthalpy for that matter, it is always about formation of 1 mole of the compound.
Right.
So here you have the coefficient as 1, right?
Yes, sir.
Retain it like that. Just because you're having a 1.5, you want to make it a whole number, you multiply it by 2 is not recommended.
Right.
Clear? Then because this will become what then? 2 moles.
Right.
So whatever be the change in the amount of heat, that is called enthalpy of formation. What is meant by this? The total heat of the products minus the total heat of the reactants. So what is enthalpy of formation?
Total heat of the reactants minus total heat of the products.
No, it is the reverse, right? Always it is products minus reactants. Clear?
Yes, sir.
Okay. So the enthalpy of formation is the heat change involved in the formation of 1 mole of the compound. This is very important. From its constituent elements. This is the definition. So what is enthalpy of formation?
The heat change involved in formation of 1 mole of a compound and its constituent elements.
Yes. The important points here are, of course, it's the heat change in formation of how many moles?
1 mole.
From its
Constituent elements.
Yes, very good. Right. One more point that you can note down in enthalpy of formation is enthalpy of formation of compounds in their naturally occurring state is 0. usually represents enthalpy of formation, which with the symbol delta HF. The enthalpy of formation for compounds or elements in their naturally occurring state is 0. Why is it so? See, when I say heat change, it means what? The amount of heat that I have to give to the system or the amount of heat that is released from the system, correct?
Yes, sir.
So either it is an endothermic process or a...
Exothermic process.
What is an endothermic process?
Endothermic process is where heat is absorbed by the system, and exothermic process is where heat is released by the system.
Exactly right. So point is, when a compound is in its naturally occurring state, I don't have to supply energy.
Right.
Or there is no energy released in the formation of it, right?
Correct, sir.
So therefore, the enthalpy of formation of such compounds will be 0. Is that clear?
Yes, sir.
For instance, oxygen. Oxygen naturally occurs in the form O2.
Yes, sir.
Correct? So for O2, for oxygen, O2, what is the enthalpy of formation? 0. Clear so far, Sambal? Any doubts?
No, sir. All clear.
Good. That's an important point with regard to enthalpy of formation. Next, we look at enthalpy of a reaction. This is kind of the most important in terms of any problem that may be asked. Okay. If you look at all these definitions, although they are kind of they look like they are different, they're all one and the same. You will understand that. Okay.
Yes,
With
sir.
minor, the variation in the way you define them. Okay. So what is enthalpy of a reaction? You can either say the heat change involved in the formation of products from the reactants, or simply you can say enthalpy of a reaction is nothing but difference, basically a subtract. So for enthalpy of reaction alone, you don't have that restriction of 1 mole. For everything else you have, okay?
Right.
So what is enthalpy of reaction? It's nothing but difference in enthalpy. When you say enthalpy, what does it mean?
Enthalpy is heat.
Heat change.
Heat changing.
Right? So difference in enthalpy of products and the reactants. So first it is products, then the reactants.
Right, sir.
How do you represent this? You represent it as simply delta H. And it is nothing but sigma delta H of formation of products minus delta H of formation of reactants. If you have to give a detailed definition, then how do you do that? It is nothing but sum of all enthalpies of formation of the products minus sum of all enthalpies of formation of the reactants.
Right.
For example, Let us take an example here. Carbon combining with oxygen, let's say, gives carbon dioxide. All right.
Right, sir.
Now the delta H for this reaction is given by, come on, tell me.
Sum of all enthalpies of formation of products minus sum of all enthalpies of formation of reactants.
Exactly. So here, what is the product, Samuel?
Here the product is carbon dioxide.
Yes. So enthalpy of formation of carbon dioxide minus what?
Enthalpy of formation of reactants.
What are the
Carbon and
reactants?
oxygen. Carbon and oxygen.
Yes. So enthalpy of formation of carbon plus enthalpy of formation of
Oxygen.
oxygen. Is that clear, Samuel?
Plus.
So this is how you write it. This is a very, very important, enthalpy of a reaction. All right.
Right, sir.
Now, obviously, of course, beyond this, you can say, this the second factor becomes zero. Why does it become zero? Because oxygen in its naturally occurring state, enthalpy of formation is what?
0.
Yeah, we had seen that, right? So anyways, so did you get an idea here? Enthalpy of reaction.
Yes, sir.
So here, there is no specification that, the product must have 1 mole or the reactant must be 1 mole. Nothing of that sort.
Okay, sir.
Okay, right. Next. Enthalpy of combustion. The word combustion, the moment you see the word combustion, what comes to your mind? Yes, Samuel? What is combustion?
Combustion is a heat change involved in heating up of a substance. The burning of a substance.
In what? We discussed that yesterday. Burning in oxygen is called combustion. Did we not discuss that question yesterday? Acetylene, combustion reaction of acetylene, correct?
Right.
How much volume of oxygen will be required for burning 520 gram of acetylene, correct?
Yes, sir.
Yes, okay. So enthalpy of combustion. So here definitely we write, right? So how do you say define this? See, I'm giving you a skeletal definition. Obviously, I want you to refer your book for every word, right, which is given in the definitions, right? Clear, Samuel?
Listen.
Okay. I'm giving the definition in a nutshell. Okay. So the heat change involved in combustion, you can use the word combustion, or you can say burning in oxygen of combustion of. Here again, how many moles?
1 mole.
Yes. So heat change involved in combustion of 1 mole of the substance is called enthalpy of combustion. For example, if we take the same reaction what we took previously, carbon burning in oxygen to give, let's say, carbon dioxide. So here we have to be very specific. This is what, let's say, delta H is, let's say, minus 393 kilojoules.
Yes, sir.
What it says is the heat change involved in burning of how much?
Combustion of 1 mole of substance.
Yes, 1 mole of carbon. So here focus on carbon. Combustion of 1 mole of carbon. So here there need not be 1 mole. Is that clear?
Right.
Because of the balanced equation, it becomes 1 mole. But the focus is on burning how many moles?
2 moles of carbon.
Sorry, where did 2 mole come in?
1 mole of carbon.
So if I say enthalpy of combustion of methane is so much, what do I mean?
That means you're burning 1 mole of that substance.
Yes, 1 mole of methane. I don't care about in the sense, I do care, but the definition goes about, it talks about 1 mole of methane. It is not important, how many moles of carbon dioxide is formed, how many moles of water is formed. But the definition circles around burning 1 mole of methane. Of course, you can solve it only by balancing the equation. So there is no questions about that. So maybe we make it 2 moles here. So carbon is 1 carbon, 4 hydrogen atoms. How many oxygen atoms?
On the LHS or RHS?
No, RHS, tell me.
RHS, there are 4.
4, right? So here there are only 2. So what do you do?
Add 2 on the LHS.
That's all. Now it's a balanced chemical equation, correct?
Yes.
So this reaction, whatever be the heat change involved, this will be called as what?
Delta H.
That's right. What is it going to be called as? Enthalpy of combustion of
1 mole of that substance.
yes.
1 mole of methane.
Yes. Okay. All right. Yes, so for sample?
Yes.
Yes. Okay. Now, like that, you have enthalpy of hydration, enthalpy of solvation, enthalpy of neutralization. What do you mean by hydration? What do you mean by hydration? Yes, Samuel.
So when an anhydrous salt like AlCl3, FeCl3, etc., when it combines with water molecules, it forms a salt, an anhydrous salt. That's hydration.
Right. Anhydrous, if you add water, does it still become anhydrous?
Hydrated salt.
Hydrated, yes. So it doesn't need to be anhydrous. It could be already hydrated. You may add more molecules of water. Yes or no?
Right.
Okay. So it's not restricted to salts also. Correct?
Yes.
Hydration. I asked you what is hydration. Hydration is simply addition of water molecules. That's it. Clear, Samuel?
Yes.
Okay. Let's say I have a compound. Let's say I add 2 molecules of water to it. Let's take the example that you have given, right?
Right.
Let's say it was initially anhydrous. It becomes hydrous. Okay. Hydrated salt right now. No problem. So the point is, enthalpy of hydration is what? Addition of water molecules to what? 1 mole of the substance.
Right.
Is that clear?
Yes.
Yes. So I am skipping the definition. So how would the definition go? The heat change involved in
Formation of 1 molecule.
not formation.
1 mole.
Hydration of not 1 molecule. What?
1 mole.
1 mole of the substance. Is that clear?
Yes.
For example, copper sulfate, anhydrous copper sulfate, consuming 5 moles of water, becoming hydrated copper sulfate, let's say. How many moles of copper sulfate is undergoing hydration? 1 mole.
Right.
Enthalpy of
Neutralization.
neutralization, right? Again, it refers to the heat change involved in neutralization of 1 mole of an acid, let's say. For example, the acid is HCl. Let's say it combines with sodium hydroxide base to give sodium chloride salt
and water.
water. All right. So if I'm talking about enthalpy of neutralization of sulfuric acid, sorry, let's say hydrochloric acid, I'm talking about how many moles?
1 mole.
1 mole. Is that clear? Usually, enthalpy of neutralization of a strong acid versus strong base is a fixed number. It is always exothermic. And this value is approximately minus 57 kilojoules.
Right.
All right. Okay. So now you've got an idea, right, Samuel?
Got it, sir.
So all of them circle around the heat change, correct?
Right.
Except enthalpy of a reaction, where the number of mole need not be 1, right?
Yes, sir.
In all other cases, we'll be talking about what? In enthalpy of formation, the focus is on the formation, which means product.
Right.
Suppose if I'm talking about combustion, the focus is on what? The reactant.
Yes.
The reactant is burnt in oxygen to give a product.
Correct.
All right. Okay. So with this basic, we'll get into the questions now. Any doubts in what we have discussed so far?
No, sir. Okay.
Sure?
Sure, sir.
Okay, great. So now let's look at the question here. See, because you will understand this best when we look at applications, correct?
Right.
Okay. So heat of formations of carbon monoxide and carbon dioxide are minus 26.4 kilocalorie, minus 94 kilocalorie respectively. What will be the heat of combustion of carbon monoxide? So what is the question? Find out.
Heat of combustion.
Find out the heat of combustion of carbon monoxide. So can you tell me what do you mean by combustion of carbon monoxide?
The heat change involved in combustion of 1 mole of carbon monoxide.
Very good, right? 1 mole of carbon monoxide. What do you mean by combustion?
Combustion is when a product is burned to give its
Not
reactant.
product, not product. A substance.
When the substance burns in oxygen to give its products.
Give some product, right? So what is the substance here?
Carbon monoxide.
How many moles of it?
1 mole of it.
Yes. So the focus is on carbon monoxide, burning 1 mole of it. So under no circumstance should you change this number here.
Right.
Okay. So carbon monoxide, you are burning it in what?
Oxygen.
Yes. Give you what?
Carbon dioxide.
Yes. So carbon monoxide will burn in oxygen to give
Carbon
carbon
dioxide.
dioxide. Correct. Is it balanced equation?
No.
No, right? Is the number of carbon atoms balanced?
Yes.
Is the number of oxygen atoms balanced?
No.
What do I need to do? Tell me, what do I need to do to balance it? No, look at the board and tell me. No need to solve, right? It's a very simple stuff. Why do you wonder? Just multiply this with half. That's it. Why?
Get 0.5 moles of oxygen.
So what do you get? How is it balanced? Tell me. You have one oxygen atom here.
Right.
2 to 1 by 2 is what?
1.
So 1 plus 1?
2.
You have 2 here. Is it clear to you?
Yes, sir.
Yeah.
Excuse me, sir.
Yes.
Sir, will you be sending these questions, sir?
Yeah, I'll be sending you these questions. Yes, sure.
Okay.
Clear, Samuel?
Yes, sir.
Yeah, balancing, there is no doubt, right?
No, sir.
Okay. Now, so you should not, what you should not do, okay, I have a fraction here, so I'll multiply the whole equation by 2. No. You should not do it here in thermodynamics. Why? Did you understand what I'm talking about? Am I audible, Samuel?
Audible, sir.
I'm not getting your response at all. What did I say you should not do?
Should not multiply the entire reaction with half.
Half,
Multiply the entire reaction with 2.
why would you do that? Why would you have a tendency to multiply it with 2? Why am I mentioning that here? See here, you don't want to deal with fraction, right, usually.
Right.
So you'll multiply it by 2, correct?
Yes.
So 2CO plus O2 will give you 2CO2 is more comfortable to deal with, correct?
Right.
But you will do it in any other chapter, but not in thermodynamics, I'm saying. Why? Didn't I tell you that you should not change this guy?
Right.
Because when I say heat of combustion, I'm talking about how many moles of carbon
1
monoxide
mole.
is burning.
1 mole.
Yeah, so when you multiply by 2, what will happen?
That one will
It
get
becomes 2 moles, right?
Yeah.
So you wouldn't want that. That's the reason you will keep, if fractions are coming, you will retain them like that. Make sense?
Yes, sir.
Yes. Okay. So now you need to find out the enthalpy change in this reaction or the heat change. So this is asked. So which concept do we need to use here? Very simple. We need to use enthalpy of a reaction.
Right.
So how do you find the enthalpy? How do you find enthalpy?
The sum of all enthalpies of the formation of products minus sum of enthalpies of all formations of reactants.
Very good. Very good. So sum of enthalpies of formation of products. So here, what is the product?
Here the product is carbon dioxide.
Correct. Minus sum of enthalpies of formation of,
Formation of reactants.
yeah.
Which is
What are the
carbon
reactants?
monoxide. Carbon monoxide and oxygen.
Yes. And as discussed, what is going to be the enthalpy of formation of oxygen? It is not even given in the question, correct?
Right.
What is given in the question?
Heat of formation
Heat
of
of formation of carbon monoxide is given. Heat of
and
formation
carbon
of carbon
dioxide.
dioxide is given. But what is not given?
Oxygen. Heat of
Okay.
formation.
Yes, but how, what do you substitute here? It's not given, right?
Right.
How do you deal with it? Didn't I tell you that the heat of formation of oxygen in its naturally occurring state is 0?
Did you write that down? Then open your mouth and tell.
Oxygen exists as O2. I told you, right?
Right.
And when a compound is existing in its naturally occurring state, there is no heat involved in its formation, correct?
Yes, sir.
I don't have to supply heat or I don't have to remove heat, correct?
Right, sir.
So enthalpy of formation is 0. That's why they have not given in the question.
Right.
Clear, Samuel?
Listen.
Okay. So it becomes a very, very simple question to you now. Enthalpy of formation of carbon dioxide, what is it? It's given. How much?
Minus 94
That's all.
kilocalories.
You just need to plug in that value. So minus 94.0. So that's 94 only. Kilocalorie minus, what is the enthalpy of formation of carbon monoxide?
Minus or minus 26.4
Very good, very good. You should
kilocalories.
not, miss out that minus of minus. Correct. Good.
So you get minus 67.6 kilocalories.
That's all. Because it is minus of minus, so it becomes minus 67.6 kilocalorie, which is the second option. So do you understand now how to solve such questions?
Yes, sir.
Is it simple? Clear?
Clear, sir.
Good, good. Shall we move on?
Sure, sir.
Yes. You've taken down the previous one sample, you've completed, right?
Yes, sir.
Yeah. Now let's move on to the next question. Consider the reaction hydrogen combining with iodine to give 2 moles of HI. The delta H for this reaction is minus 12.4 kilocalorie. According to this, the heat of formation of HI will be. Extremely simple question. Yes, sir. So you are given this reaction, correct, Sam?
Yes, sir.
What is that you are asked to find?
Heat of formation of HI.
Yes. Can you define what is heat of formation of HI? Heat of formation can also be called as enthalpy of formation of HI.
Right.
How do you define that?
The heat change involved in the formation of 1 mole of the compound is always equal to its constituent reactants.
What?
Elements.
Is always equal to 1. What are you saying?
No. The heat change involved in formation of 1 mole of 1 mole of the compound from its constituent elements.
Yeah. So heat change. Now apply this definition to this question here.
The heat change involved in formation of 1 mole of HI is 1 mole of HI from its constituent elements.
Very good. What are its constituent elements?
Hydrogen and iodine.
Correct. Very good. So can you write an equation for heat of formation of HI? And tell me. Do you remember like we wrote for calcium carbonate?
Yes.
Now you write the equation for heat of formation of HI and tell me the equation.
H plus I forms HI.
Does H plus I form HI? See here, you can't write H plus I, correct? Yeah, it is not H, right? Nascent hydrogen is not there, right? Got it?
Yes.
Is it correct?
But the equation is not balanced.
It's not balanced. So what do you do to balance it?
Add 2 on the RHS.
Can you tell the definition once again and tell me what I should do? Define the formation of HI.
The heat change involved in formation of 1 mole of HI from its constituent elements, hydrogen and iodine.
Repeat. Slow down and repeat.
Oh, okay. The heat change involved in formation of 1 mole.
Formation of?
1 mole of HI.
Okay, repeat now. Repeat.
The heat change involved in formation of.
Stop. Slow down very well. Very much.
1 mole.
Of what?
Of HI.
Repeat that part again.
1 mole of HI.
Repeat it again.
1 mole of HI.
Yes. So can I multiply that number 2 to HI?
No.
Did you understand now?
Right. Because
should not do this. Is that clear?
Right.
So what should you do now? Alternately.
Keep it as 1.
Yeah, you must keep it as 1. No questions about it. But you should still balance the equation. So what do you do?
Add 1 on the RHS 2. LHS.
Add 1 on LHS. See, this guy must be 1, correct?
Yes.
That you should not touch. That's why I asked you to repeat the definition 3-4 times. But you still should
1 by
balance,
2.
right? Is it balanced right now?
No.
So what do you do?
Add 1 by 2.
Don't say add. Okay. So what do? You make it?
1 by 2.
Yes. For what?
H2.
What about I2?
Same thing.
Yes, this is correct. Is it clear now, Samuel?
Yes,
You
sir.
must watch out for this. You should never add 2 there. Are you clear? Because definition says it's 1 mole of HI, correct?
Yeah.
Yeah. So now let me write that equation here next to this. So half mole of H2 combining with, come on,
Half mole of I2 bonds 1 HI.
let me call this delta H as delta H1. This is what is asked.
Right.
Isn't it? I said the sum is a piece of cake. It's very, very simple, right?
Yes, sir.
Yeah. Why did I say that? Because now chemistry is over. Now very simple mathematics. 2 chocolates cost 10 rupees. 1 chocolate?
5 rupees.
Yes, that's all. So what is this equation? Can you tell me what is this reaction? The heat change involved in formation of?
1 mole of HI from
No, this reaction I have marked in green. What is it? Read it carefully and tell me.
the heat change involved in formation of 2 moles of HI from
Very
its
good.
constituent elements, hydrogen and iodine.
No, don't worry about it. Yes, correct. But then, you can just, so is this enthalpy of formation?
No.
No, very good. So as you rightly said, it is heat change involved in formation of
2 moles of HI.
2 moles of HI from its constituent elements, correct? So that value is this, correct?
Yes, sir.
Keeping this in mind, what do we want?
1 mole.
We want it for 1 mole. So what should I do?
Divide that by 2 and you get 6.20 kilocalories.
That's your answer. Minus. So isn't it simple?
Yes, sir.
Yes. There is also one enthalpy which I have not, there are a few enthalpies which I have not discussed. You can go through in the text, but then they all follow similar definitions. So probably one definition, one question I'll ask you right now at this point, without, without giving the definition, but I expect you to get what should be the definition and what would be the answer. Okay. So let me ask same question. Okay. The reaction H2 plus I2 giving 2HI, delta H is minus 12.4 kilocalorie. According to this equation, the second part of the question I'm going to change. What is the heat of dissociation of HI? What is my question?
Heat of dissociation of HI.
Yes. So can you frame the definition for heat of dissociation of a compound? What do you mean by dissociation?
Where a compound just dissociates into its constituent elements.
Very good. Very good. That's all right. So can you tell me what will be the definition for heat of dissociation or enthalpy of dissociation? Tell in your own words. Think about it and tell in your own words. Even if you make mistakes, it's okay.
The heat change involved in the dissociation of 1 mole of its compound into its constituent elements.
Very good. Excellent. Right. So now, can you write the equation for heat of dissociation of HI? And tell me.
One HI forms half H2 plus half I2.
Excellent, excellent. That is your equation for dissociation of HI. Is that clear?
Yes, sir.
Very good. You must keep it 1 mole, right? Very good, which you have kept. Good. Now, can you also guess? Can you also guess? Okay. What would be the enthalpy for that?
So the enthalpy of formation, if I'm correct.
Not enthalpy of formation. What am I asking?
Dissociation, sorry.
Enthalpy of dissociation of HI. You got the equation right. Very good. HI
Okay.
giving half H2 plus half I2. Correct?
Correct, sir.
Now I'm asking you what would be the enthalpy. Can you compute it from the given data?
So do I tell the answer or the formula?
Now tell me the answer. There is no formula, right? I mean,
Okay.
tell me the answer.
Okay. Minus 6.20 calories, kilocalories.
See, that is for this heat of formation, correct? That we already calculated, right? Yes or no?
Yes, sir.
What am I asking you?
Heat of dissociation.
Correct? Yeah. For that also, do you say it is minus 6.2 kilocalorie?
No.
Okay. I'll help you out, right? See here, if a forward reaction is exothermic, the reverse reaction will be endothermic.
Right.
So formation of HI, what do you say? We just got it as what, minus 6.2 kilocalorie?
Yes. Yes, sir.
Is it exothermic or endothermic?
Endothermic.
No, don't simply say. Delta H value is negative, means it is exothermic. Delta H value is negative for a reaction, implies it is exothermic.
Right.
Delta H value, enthalpy value is positive for a reaction,
Endothermic.
it is
Endothermic.
endothermic. Why? Again, it's common sense, right? What is delta H? How do you find? Sum of heat of products minus sum of heat of reactants, right?
Yes, sir.
What is exothermic means what? The reactants, when they combine, they release energy and they form products.
Right.
So products will have lower energy or reactants will have lower energy in an exothermic reaction. In an exothermic reaction,
Okay.
will reactants have greater heat energy or products will have greater heat energy in an exothermic reaction? And why? Hmm? Yes, Samuel. See here, reactants are coming together, they are releasing heat and becoming products, correct?
Yes.
So if you release heat, you will cool down, right?
So lesser energy.
Which will have lesser energy?
The reactants.
Product, no, once it's cooling.
It's cooling and the product is formed, right? So product has lesser energy, correct? Reactants are giving away the heat and forming products.
Right.
Do you understand the point?
Yes.
Reactants, after giving away the heat, they are no longer reactants, they have become products.
Right.
Do you understand that?
Yes.
So the heat of formation of products will be less compared to the heat of formation of the reactants, correct?
Right, sir.
So heat of formation of products minus reactants therefore becomes negative because you're subtracting a bigger number from a smaller number.
Yes, sir.
Are you getting it?
Yes, sir.
Okay. Point number 2. If forward reaction is exothermic, for example, H2 plus I2 giving 2HI, or let's say half H2 plus half I2 giving HI, what did you get the delta H value as?
Sir, I'm sorry, can you repeat the question, sir?
Yeah. What is the delta H for this reaction?
Which
For the
we
heat
got
of formation of HI.
heat of formation means we got minus 6.20 kilocalories.
Correct. Right. So tell me from this, is it exothermic or endothermic? Is this reaction? Formation of HI.
If it's negative, means it's exothermic.
Yes, correct, exothermic. So I am asking you dissociation, right? Dissociation means I am asking you the reverse reaction. You got the reaction correct, right? So what am I asking? The heat involved in this reaction.
Endothermic.
Yes, so this reaction will be endothermic. Is it clear?
Yes, sir.
The heat involved will be same. The quantity of heat involved will be same. Therefore,
V plus 6.20 kilocalories.
yes. So this will also be 6.2, but only difference this guy will be plus, because if the forward reaction is exothermic, the reverse reaction will be,
Endothermic.
yes. Suppose instead of asking heat of formation of HI, if I had asked heat of dissociation of HI, the fourth option would have been right.
Right.
So did you understand the whole thing now?
Yes, sir.
Yeah. In an exothermic reaction which has more heat energy, products or reactants, quick.
Reactants.
Yes. In an endothermic reaction which has lesser energy, reactants or products?
Reactants.
Reactants as?
Lesser energy
In what?
in endothermic reaction.
Why? Because they will absorb heat and become products.
Yes.
And delta H is positive or negative for endothermic reaction.
For endothermic, it is a positive. It's positive.
Very good. Very good. Very good. Are you clear now?
Yes, sir.
Good. Okay. Let's move on to the next question. Okay, ma?
Yes, sir.
Yeah. Now go through this question. You are given some data, right? Can you
Yes.
tell me, can you define, right? You are given a data in the first part, right?
Yes, sir.
Can you tell me what is given?
Enthalpy of combustion of benzene.
Combustion. Combustion means you should have oxygen. Are you having oxygen here?
No. Carbon and hydrogen are forming benzene.
So what is it?
6C plus 3H2 forming CC6.
What do you define it as?
The heat change involved in formation of 1 mole of benzene from its constituent elements.
So what is it called?
It's called enthalpy of formation.
Enthalpy of formation of what?
Benzene.
Very good. Yes. Next.
The heat change involved in formation of 1 mole of water from its constituent elements.
Very good. So what do you call that?
That is also called heat of formation.
Yeah, heat of formation or enthalpy of formation of what?
Heat, formation of water.
Very good. What is the next one?
The heat change involved in formation of 1 mole of carbon dioxide from its constituent elements. That's called heat of formation again.
Yeah, enthalpy of formation of carbon dioxide. Is there any other way you can define third equation? Enthalpy of formation of carbon dioxide is correct. But is there any other way to call it?
Combustion. Enthalpy of combustion.
Enthalpy of combustion of what?
Of carbon dioxide.
Not carbon dioxide. You're not burning
Of oxygen, sorry, of oxygen.
You're not burning oxygen, man.
Carbon in.
Carbon and oxygen.
You're burning carbon in oxygen, correct?
Yes.
So is it enthalpy of formation of what?
Carbon and oxygen.
You should not say oxygen.
Carbon.
If I say enthalpy of formation, it's enthalpy of combustion, oxygen is a known factor, right? Should
Carbon.
not put oxygen.
So it's carbon.
Do you understand why I'm saying you should not talk about oxygen? Because whatever you're speaking about, that should be maintained as 1 mole.
Right.
Do you understand what I'm saying? You can't maintain two compounds, molar ratio as 1, yes or no?
Right, sir.
Correct? So if I say enthalpy of combustion of methane, what is the meaning?
Here oxygen is carbon is burned with oxygen.
What? Forget this question now. I'm asking another question. When I say enthalpy of combustion of methane, what do I mean? I am burning methane in oxygen, correct?
Yes.
Enthalpy of combustion of acetylene.
Burning acetylene and oxygen.
Yeah, so will I be able to maintain the ratio, maintain the molar, stoichiometric coefficient as 1 for oxygen?
No.
So what should I maintain it as 1?
Methane, the carbon.
Not carbon, man. So I'm talking about that equation, methane. So you should
Methane. So methane is maintained as 1.
Yes, what about acetylene?
Also maintained as 1.
Correct. So here, like that, which one you should focus on?
Carbon.
Yeah. So what is this called? So tell me the two definitions for ethane. Third equation.
Both the definitions, sir.
Yeah, both of them.
Okay. The heat change involved in formation of carbon dioxide from its constituent elements.
Don't
That's
miss the 1 mole.
from 1 mole.
Wait.
Okay, then we have enthalpy of
No,
combustion.
first tell me that definition clearly.
The heat change involved in formation of 1 mole of carbon dioxide from its constituent elements.
Which is called
Enthalpy of formation.
of
Formation
enthalpy formation of what?
of carbon dioxide.
Then you must mention clearly, please. Very good. First definition correct. Second definition. Second definition for the same stuff. You just did that.
The carbon, when carbon burns in oxygen to form 1 mole of carbon dioxide, it is called enthalpy of combustion of carbon dioxide.
Repeat what you said.
It can be defined, enthalpy of combustion can be defined as the heat change involved in 1 mole of carbon dioxide.
Combustion of 1 mole.
Combustion of what, Samuel?
Or 1 mole of carbon dioxide.
Are you burning 1 mole of carbon dioxide?
1 mole of carbon.
Why do you're messing it up? Are you getting the point? So can
Yeah.
you tell the second definition correctly?
The heat change involved in combustion of 1 mole of carbon.
Yes.
From
Not constituent. What from what? From
no,
nothing.
from the substance.
What from the substance?
What is the general definition? Here only stick to that.
Tell me, Samuel.
The heat change involved in combustion of 1 mole of carbon.
Yes. To form carbon dioxide. That's fine. Okay. So 1 mole is where?
For the third reaction.
For the third reaction, second definition, 1 mole when you say is applicable to which compound?
Carbon.
Carbon. When you say combustion. When you say formation, 1 mole is applicable to what?
Carbon dioxide.
Yeah, we must be very, very, very clear about that. Is that clear, Samuel?
Yes.
Okay, good. So now tell me this question. Enthalpy of combustion of benzene from the following data. So what do you need to find here?
The enthalpy of combustion of benzene.
What does that mean?
This means it's in the first case. The
First
combustion of 1 mole of benzene.
First case, if you have to find means it's already over, right? Sum is over.
The heat change involved in combustion of 1 mole of carbon from it.
Read the question.
The enthalpy of combustion of benzene from the following data.
Okay. A combustion of benzene means what?
Combustion of 1 mole.
Do you have the equation for that? What is
Yes.
the equation for that? Tell me.
6C plus 3H2 forms C6H6.
Is that combustion of benzene, Samuel?
No.
I'm asking you what will be the equation for combustion of benzene? What do you mean by combustion of benzene? What is the equation for combustion of benzene? Do you have it here? If it's not there, you write it down and tell me. Now don't copy down these equations. I want you to frame the equation for combustion of benzene. What is combustion of benzene? Combustion. What do you mean by combustion?
When you burn carbon with oxygen.
Not carbon. Repeat this 5 times. Combustion means burning in oxygen.
Combustion means burning in oxygen. Combustion means burning in oxygen. Combustion means burning in oxygen. Combustion means burning in oxygen. Combustion means burning in oxygen.
Okay. If I say combustion of benzene, what does that mean?
Burning in oxygen. Burning benzene and oxygen.
Repeat that 5 times.
Burning
Combustion of benzene
benzene.
means?
Burning benzene and oxygen. Same thing, sir.
Yes.
Burning
Combustion
benzene.
of benzene means?
Combustion of benzene means burning benzene and oxygen. Combustion of benzene means burning benzene and oxygen. Combustion of benzene means burning benzene and oxygen. Combustion of benzene means burning in oxygen.
Burning?
Burning benzene and oxygen.
Yeah. Burning benzene in oxygen means how will the equation look? Benzene in oxygen. How will it look?
C6H6 plus O2.
Good. What will be the product? Next thing you have to think about is what is the product? What will be the product? Didn't I tell you? If you burn methane in oxygen, what do you get? Same product. If you burn ethane in oxygen, you'll get same product. If you burn ethene in oxygen, you'll get the same product. If you burn acetylene in benzene, you'll get the same product. If you burn benzene in oxygen, you'll
Same
get
product.
what product?
Benzene again.
You burn benzene in oxygen, you'll get benzene again.
How will you get benzene, sir?
Didn't I not tell you yesterday?
No.
Any hydrocarbon you burn in oxygen, you get carbon dioxide and water. Repeat that 5 times. Any hydrocarbon I burn in oxygen, I get carbon dioxide and water. Tell me.
Sorry, sir, can you repeat again? Got stuck.
Any hydrocarbon.
Right.
Hydrocarbon means what?
Combination of hydrogen and carbon.
Yes, that means methane, ethane, ethene, acetylene, benzene. What is benzene? C6H6. What is it? It's a combination of
Carbon and hydrogen.
any combination of hydrogen and carbon. You burn it in oxygen, you will only get 2 products. What are they?
Carbon and hydrogen.
What?
Carbon dioxide.
Carbon dioxide
water.
and water.
Okay, repeat this 5 times. Probably I would recommend 10 times also, but right now 5 times. This is why revising is very important, Samuel, because it's extremely important. Once you revise it, if it's there in your head, this sum is nothing. Right? Okay, go ahead. Burning any hydrocarbon in oxygen gives me, this is 10th standard. Haven't you learned in hydrocarbons in 10th standard? Alkanes burning in oxygen? I'm sure you have. Correct?
Yes.
Yeah.
Yes.
So it's important that whatever you learn, it must get in. You must ensure that it gets in. Right? So if I'm made to repeat what I said yesterday, it's a waste of time for all of us. Yes or no?
Right.
And more importantly for you, right? You are attending the class but not revising. Then what happens is, that class is wasted, in my opinion. Correct, Samuel?
Right, sir.
Yeah, please do revise, okay? So listen now. Because it's all simple. It's no big deal. If you remember a few things, it's all simple. Piece of cake. Okay, go ahead. Tell me now, 5 times. Because 12th also you'll learn all these things. Come on, tell me. Combustion means what?
Combustion means burning of any compound in oxygen.
Good. So the moment I say combustion, you will write that compound plus oxygen. Clear?
Yes.
Now the next part I want you to be thorough. Any hydrocarbon, tell me.
Any hydrocarbon.
If I burn in oxygen.
If I burn in oxygen.
The products will be.
The products will be.
Carbon dioxide and.
Water.
And nothing else.
Right.
Tell this 5 times.
Any hydrocarbon, when I burn with oxygen, it will give carbon dioxide and water.
And nothing else. Okay.
And I had to tell that also.
Yeah, tell. Doesn't matter. So it kind of gets into your head.
Yes.
5 times.
Any hydrocarbon, when burns in oxygen, it gives carbon dioxide and water and nothing else.
Very good. Go ahead.
Any hydrocarbon which burns in oxygen gives carbon dioxide and water and nothing else.
Tell me the intensity, okay? Don't tell it on the surface. Because every word you utter with involvement, that is a difference. That's the difference. Go ahead.
Any hydrocarbon which I burn in oxygen, it will give carbon dioxide and water and nothing else. Any hydrocarbon which I burn in water gives, which I burn in oxygen gives carbon dioxide and water and nothing else. Any hydrocarbon which I burn in oxygen gives carbon dioxide and water and nothing else.
Very good. So now you know the equation, right? So when I say combustion of benzene, before balancing, can you tell me the equation quickly? combustion of benzene. So what must be the reactants?
C6H6 plus O2.
Very good. Then immediately what?
Carbon dioxide and water.
Good. That's all. I don't think you'll forget it going forward, correct?
Yes, sir.
Good. So now next step is balancing. Now balance it and tell me. Which one you must make sure you maintain it as 1 mole. So in these reactions in thermodynamics,
Right.
you have 4 substances here, right? Benzene, oxygen, carbon dioxide, water. Whose stoichiometric coefficient you must maintain it as 1 no matter what?
Carbon dioxide.
Is it combustion? Read the question again. Combustion of?
Benzene.
Read it 5 times.
Combustion of benzene, combustion of benzene, combustion of
Slowly.
benzene,
Combustion of benzene. Like that you say.
combustion of benzene, combustion of benzene, combustion of benzene, combustion of benzene, combustion of benzene.
Combustion of?
Benzene.
So whose stoichiometric coefficient you must maintain as 1?
Benzene.
Benzene. What did you say? You said carbon dioxide.
Yes.
Is it making sense or not, Samuel?
Sammy,
Yes,
what
sir.
is asking? Leave the pen cap, it's okay.
Yes,
So
sir.
if I say hydration of sodium hydroxide, which one would you maintain 1 mole?
Sodium hydroxide.
If I say formation of carbon dioxide, which one would you maintain 1 mole?
Carbon dioxide.
Yeah. If I say neutralization of HCl, which one will you maintain 1 mole?
HCl.
Understood?
Yes, sir.
So combustion of benzene, which one would you maintain 1 mole?
Benzene, obviously.
Yes. Is that clear? So why am I stressing this? Because by no matter what, you must not change this
Right.
in an attempt to balance the equation. Go ahead. And tell me the balanced equation.
Yes, C6H6, that remains 1. I need to balance hydrogen. 3H2 means 6 hydrogen, 3O is 3 oxygen, 5. So can we put 2.5 for oxygen on the LHS?
You tell me, can we or we cannot?
No, I'm saying for oxygen.
Whatever, right? Can you make it fraction?
5 by 2.
Hmm?
5 by 2.
But yeah, fraction or decimal does not matter, right? Yeah, of course. Of course, in thermodynamics, you can make any coefficient to be fraction in order to maintain 1 mole for that component, which is very important, right?
Right.
Your combustion of benzene is what?
Combustion of benzene.
So you need to maintain 1 mole for what?
For benzene.
Yeah, rest of it you can do it you can make it decimal, does not matter.
Yes, sir.
So can you tell me the balanced equation if you've already completed? See, after balancing it, check every element whether it's balanced or not.
Carbon is not balanced still.
No, you must balance it and tell me.
Yeah, that's all right.
Yeah. Balancing chemical equations also you've learned in 8th standard, right? Anyways, it doesn't matter, right? But right now, at least it's the time that you should be thorough with it.
Right.
Yes, Samuel, go ahead. So much time is not needed at all. You can just finish it in a few seconds.
C6H6
Hmm.
plus 5/2 O2. 5/2 O2
Hmm.
forms CO2 plus 3H2O.
If it is CO2, you already said carbon is not balanced, right? If it is only CO2, is carbon balanced, Samuel?
No.
Balance it and tell me. No, balancing means what? Whatever is on the left hand side, you should have it on the right hand side, correct or not? Number of atoms.
Correct.
So why are you just keeping it as CO2? What you should do? Left side, how many carbon atoms are there, Samuel?
6.
So how many carbon atoms should be there in the right side?
6.
How many are there right now?
Only 1.
Yeah, so what you should mark right away?
6.
Yeah, why are you not making that?
So then oxygen will not get balanced, right?
Forget that. Let's take care of it later, right? Oxygen is standing alone, right?
Yes.
So last thing that you will balance is oxygen.
Okay. So
And
6
standing
CO2.
alone, you can deal with very easily, right?
Yes.
Go ahead. So why are you stuck on 5/2 for oxygen?
What, sir?
No, why are you stuck on 5/2 for oxygen? You get my point, and you're not balancing carbon. So go ahead, tell me now.
One C6H6 plus 5/2
No,
O2
5/2 is not correct, obviously, right? So forget that. Tell me CO2.
forms 6 CO2 plus 3H2O.
Right. You're done with that. Carbon is over now.
Okay. So
How many carbons on the left?
6 on the
How
right.
many carbons on the right?
6.
How many hydrogens on the left?
6.
How many hydrogens on the right?
6 again because 3
Over
times.
right. Over right.
Yes.
Now oxygen is only not balanced, correct?
Yeah.
So what is on the right? Tell me what is on the right. How much is on the right?
So we have
Simple multiplication.
they have 15 oxygen atoms on the right.
That's all right. You have 15 oxygens on the right, correct?
Okay.
So how many oxygens should you have on the left?
15 O2. 15
15
oxygen
out of
atoms.
this, you'll get 30, man. Listen here. This
15.
is 6, correct?
Okay.
This is 3, correct?
Yes.
So how many oxygens do you have on the left and right hand side?
15.
How many do you need here?
We need 15.
How do you get 15? Already 2 is there.
Yes.
And how do you get 15?
7.5. 7.5.
That's all. What is 7.5? If you want, you can write as
15/2.
7.5 or 15/2. Doesn't matter. This should be done within 10 seconds, Samuel. Is that clear? I'll just give you an assignment exclusively on this. Probably 10 equations where you will only combustion. Okay.
Yes, sir.
Yeah, fine. So is that clear, Samuel? Because these things are should not take more than 10 seconds for you to do it. Okay.
Yes, sir.
Otherwise, you'll be stuck in this and you'll not do the sum. There'll be
Right.
probably half a mark for writing this equation, correct? In a 5-mark question.
Right, sir.
Yeah, this you must see that you're doing it. It's not difficult, right?
Right.
Is it easy or not? Isn't it easy?
Yes, sir.
I don't see any difficulty in this. Correct or not?
Yes, sir.
Yes, sir. Okay, good. Now move on. Now, so this is the equation you want to get. So now tell me, we need to find the enthalpy of combustion. That means we need to find the enthalpy of this reaction. How do you do it? You have a reaction. How do you find the enthalpy, Samuel? What is enthalpy of a reaction? Because the moment you got the reaction, sum is over, in my opinion.
So difference in enthalpy of products and reactants.
Very good. Good, good. So let's do it here. So delta H for the reaction is delta H of formation of products minus,
Delta H formation of reactants.
yes, Okay, now what are the products now? What are the products?
Carbon dioxide and water.
Very good. And what are the reactants?
Benzene and oxygen.
Very good. So you should add the formation of products, right? First, correct?
Right.
So you'll add the formation of which product first? Whichever, doesn't matter. So tell me the products.
Carbon dioxide and water.
Right. Clear, Samuel?
Yes, sir.
One thing you have to watch out for is how many moles are there? How many moles of carbon dioxide are there?
6.
Yeah. So this delta H of formation, whenever you say heat of formation, it refers to how many moles?
Heat of formation was generally to 1 mole.
Yes, 1 mole of that compound, right?
Yes.
So for 1 mole, it is delta H. For 6 moles, it will be
6 times that.
very good. So that's why you should multiply with 6. Is it clear now?
Yes, sir.
Right. So here, what should you do?
So, sorry, sir. What?
For we did for delta H of carbon dioxide. Now next, delta H of
Water.
water. What should you?
3 times.
Very good. Because you are, see, do you understand that, if you don't get this equation right, going forward, it will be wrong.
Yes.
Yeah. So it's extremely important you get the equation right. Wow, fast. Okay, good. Now tell me, ma. So what are the reactants?
3, 6 benzene and oxygen.
Yeah. Benzene, how many moles?
Benzene has 1 mole.
1 mole only, right? It must be one mole, correct?
Yes.
Plus, how many moles?
7.5 moles.
Moles of oxygen.
Oxygen.
But we are not given the formation of oxygen. What should we do?
Find it out.
Okay, now imposition starts.
What?
Enthalpy
You
of
don't know the
a
oxygen.
compound in
That's
its
0.
freely occurring state, 0. Repeat 3 times now.
Sorry, sir. What? Enthalpy of
Formation of
formation of oxygen is 0.
not
Enthalpy
just
of
oxygen, you just tell the main definition. Any compound in its freely occurring state or naturally occurring state is 0.
any compound in freely occurring state or
Naturally
naturally.
occurring state. That means, for example, gold exists as gold atom.
Correct.
So formation is 0.
Yes.
Oxygen occurs as O2. So formation is
0.
This is the third sum where we are dealing with this, correct?
Right.
And you said we should find it out.
Yes.
There is no need to find out. What is the answer?
0.
Correct? So now repeat 2-3 times. Go ahead.
Enthalpy of formation of any substance occurring freely or in its naturally occurring state is 0.
Any substance in its naturally occurring state is 0. Please tell me, ma, another 2 times.
Any substance in its
No,
naturally
not enthalpy of.
enthalpy of any substance in its naturally occurring
Enthalpy of
state.
formation of. Enthalpy of formation of. Go ahead.
Enthalpy of formation of any substance in its naturally occurring state is 0.
Yeah, again.
Enthalpy of formation.
Slowly. Enthalpy of formation of.
Enthalpy of formation of any substance in its naturally occurring state is 0.
Very good. Is it
Enthalpy of
clear now? Good.
yes.
Good. Yeah, complete.
Enthalpy of formation of any substance in its naturally occurring state is 0.
So enthalpy of formation of oxygen will be
0.
right. Okay. Now we are almost there. All data which is required is already available with us. So come on, tell me, Samuel. 6 times delta H of formation of carbon dioxide. Where do you pick the data from? Heat of formation of carbon dioxide. What is the equation? Formation of carbon dioxide. Which is the equation? Is it not
Third
this?
equation. Third equation.
What is the enthalpy?
Minus 393.5.
Yes. So in place of this, what should you substitute?
Minus 393.5.
Yes. Then what? 3 times?
Minus 285.9.
Very good. Minus. Minus of what?
Minus 1 into 45.9.
Yes. Calculate and tell me the final answer.
Okay, sir.
So this is a potential detail answer question, right?
Yes, sir.
But once
Just
you,
solve it.
yeah, tell me, ma.
I'll just solve it, sir.
Yes, yes, please. Is it very difficult, Samuel?
No, sir, I'm doing.
It's easy? No, 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 not this is solving. I'm talking about, have you been able to understand?
Just when it comes to applying that enthalpy of formation, that's the time where little confusion occurs.
No confusion. Now you're clear, right?
Now I'm clear.
Yeah. So if you get the fundamentals right, then there is no problem. These are, you can't get a simpler question than this.
Right.
Only thing is you need to be comfortable with balancing. Second thing is just substitution and multiplication, addition. That's it, right?
Right.
Yes. Any doubts in this?
No, sir.
Very good. Very good. Yes. Go ahead. So heat of combustion of glucose is given. How much will be the energy required for production of 0.18 gram of glucose by the reverse reaction? So I've already told you about reverse reaction. So first, can you tell me the heat of combustion of glucose, is it an exothermic reaction or endothermic reaction?
Heat of combustion of glucose.
Data is
Exothermic.
given. Data, observe the data and tell me.
Okay.
Yes.
Exothermic.
Very good. How did you say exothermic?
Because the change in energy in enthalpy is negative.
Very good. Very good. So you just need to observe delta H. If I ask you whether it is exothermic or endothermic, you will just focus on that reactions delta H. The value is negative, then it is what?
Exothermic.
Exothermic, right? Now, if I am doing the reverse reaction, the heat change will be same.
Right.
Only difference is that the reverse reaction will be,
Reverse reaction. Oh.
if the forward reaction is exothermic, reverse
Endothermic.
will be,
Endothermic.
yeah, tell that 3 times.
Ah. The forward reaction is exothermic, the reverse reaction or backward reaction is endothermic. If the forward reaction is exothermic, the backward reaction is endothermic. One more time. If the forward reaction is exothermic, the backward reaction is endothermic.
Suppose if the forward reaction is endothermic, reverse reaction will be, backward reaction will be?
Exothermic.
Yes. So are you clear with this?
Yes, sir.
But there will be no change in the numerical value of delta H.
Right.
So can you tell me now, the reverse reaction, can you tell me the equation?
Okay, just a minute. It's reverse reaction.
Yeah. Can you tell me the reverse reaction equation? Reverse reaction.
6CO2
Yes.
plus 6H2O forms Z6H12O6 plus 6O2.
So you should also relate, right? So are you seeing, even if you burn glucose in oxygen, what are the products you're getting?
Carbon dioxide and water.
So are you also observing, right?
Yes.
Yeah.
So,
Okay. So now the reverse reaction, you've written it. I want you to tell what will be the delta H for this.
delta H will be positive.
How much is the value?
Plus 2,840
Very good.
kilojoules.
So there will be no difference in the numerical value, but only the sign will change.
Yes.
Since the forward reaction was exothermic, the reverse reaction is going to be now endothermic. Yes or
Yes.
no?
Yes.
Okay. This can also be called as right? Not directly we cannot call it as heat of formation of glucose, right? Why? Because when I say heat of formation of glucose, it must be from its constituent.
Elements.
It can't be from the compounds, right?
Yeah.
So this equation, although it forms 1 mole of C6H12O6, I cannot call this equation as what?
For enthalpy of formation.
Yeah, enthalpy of formation of glucose. No, right? But anyway, this is an enthalpy of a reaction, correct?
Yes. Yes.
Okay. Okay. Now, here I am forming how many moles of glucose, Samuel?
1 mole.
1 mole, isn't it? 1
Yes,
mole of glucose is how many grams? Now you have to come back from yesterday's class.
I don't like the weight, sir.
1 mole of, yes, 1 mole of glucose weighs.
180 grams.
Very good, excellent, right? So, for the formation of 180 grams of glucose, now chemistry is over, okay? For the sum. For the formation of 180 grams of glucose by this reaction, delta H value is, how much is the delta H value, Samuel?
Positive.
How much value?
Oh. 2840.
Correct?
Yes, sir.
Kilojoules. But how many grams do we need?
We just 0.18.
Yeah. So for 0.18 grams of glucose to be formed through this reaction, what will be the new delta H? Maybe I'll call this delta H as delta H2. Get it for me?
2840 by 180.
This is no different from what?
2840 by 180.
Will that be the answer? Tell me the final answer now.
I have to solve, sir. 2840 by 180.
That's all?
I have to divide for them, see.
No. That is not the answer, Samuel. How do you simply divide that to? See, it is your basic 9th standard, 8th standard method, right? 2 chocolates, 100 rupees, 1 chocolate, 50 rupees. I mean 50 rupees, correct?
Yes.
So we have done this plain and day out yesterday, right?
Yes.
How should you do it? Take whatever quantity you don't know as X.
X.
Proportionality, correct?
Oh.
180 divided by 0.18. Is equal to 2840 kilojoules divided by X. We don't know X. We need to find X.
That's all, Mendelssohn.
Yeah. Thousand times. So you bring X here.
So I'm getting a X as 2.84 kilojoules.
Yes. Yes, Samuel, right? Having got to this point, simply don't divide these two and say that is the answer, correct?
Right.
So how easy it is, isn't it so simple?
Right, I thought.
Correct? Yeah. Okay. So you must recognize that this is no different from that chocolate sum which I told, correct?
Yes, sir.
Yes. So is it clear to you?
Yes, sir.
Yes, very good. If you note it down, let me know, then we'll
Done, sir.
do another question. Again, a simple question. Yeah. I'll not give you any support in this question. You will do it yourself and tell me. Okay. Clear to you? So whenever you're asked to find the enthalpy change of reaction, what do you do?
Multiply it with the amount of moles it has in the
Enthalpy
reaction.
of products, enthalpy formation of products minus that of reaction.
Reactants.
And when you write that, what you must ensure?
Ensure that how many ever moles that compound is associated with, multiply it.
Very good. You should multiply that. You should not forget to do that. Then substitute. Then substitute and get the answer. Then in the final answer, if they ask per mole, then you should look at the equation. So here 2 moles of peroxide is becoming 2 moles of water. Per mole, that means 1 mole of peroxide becoming 1 mole of water, you should divide it by 2.
Yes, sir.
So that's kind of a final twist in the question, correct?
Yes, sir.
All right. But at least these basic stuff you need to take care of. Good. Very good.